Nice. Before we jump into like word dictionary, did someone figure out how can we implement cache using MySQL? What happened?
Changing the storage engine to in memory.
Exactly. That's exactly what I was looking for. Matlab, having a large buffer pool would be a great start, but a great solution to that is ability to change. Matlab, we changing the storage engine, because that would be the best decision. So for folks who don't know about this, MySQL in general, any database has a storage engine. This storage engine would be the one who would ensure whose job is to implement the core data structures. For example, using B plus trees to have like store rows and tables and columns and clustered index and whatnot. So each storage engine has its own way of storing things. So for example, MongoDB has a famous storage engine called as Wired Tiger, right? But there are other proprietary storage engines which MongoDB offers on its cloud offering, right? Which are very proprietary to MongoDB as a company. Similarly, MySQL's default engine is called as InnoDB, which is a disk-backed database and has its own way of storing things. But there is another storage engine which is available, which just in-memory storage. So it has zero persistence. It stores everything in memory. So the primary requirement with cache is what? Like we have to have very high throughput. So get, put, delete, atomicity, everything that we discussed yesterday. If you see, all of those things come out of the box through a normal MySQL or any SQL database. So you could be tempted to use that as your primary storage. But then you'd realize ki, Array, but this is storing on disk, my cache does not need to be stored on disk. But that is exactly where the twist comes in, where the storage, where you have an option to alter the storage engine of MySQL and you can switch it to an in-memory storage engine. So if you look out for MySQL storage engines, you would find InnoDB as the default one, and there are 5-6 others which come out of the box of MySQL offering. So just change it to an in-memory one. You'll get all the benefits of SQL. You'll get all the benefits of in-memory, and you can like very bluntly implement cache on top of it, because that's what you need. Get, put, delete, and then create an index through which you can do TTL-based implementation and whatnot. So just changing the storage engine could actually work really well if you're trying to implement something like this. So a quick thing, we
Have you done
also,
it?
I've not used it for storage. Basically, that's what I was coming to. So what I did
Okay.
was just post my master's when I was working at Practo, we took up a very ambitious project on scaling up our database, but implementing key value database on top of SQL storages. It was like a very ambitious one. Like DynamoDB was there, but we still chose to implement one. So what did we wanted to do was, we were heavily reliant on MySQL, and the use case that we wanted was like we wanted to support JSON data type on MySQL. And for some reason, this was something that came from the principal architect that we had, and I was the only one who was going to implement it. So I was a fresher. I was just like 8 months, 9 months old in the industry. I was handed down this project key. Let's implement a database of our own. So that is exactly when like I was told ki we'll build on top of MySQL. So I was like, every single time I was just thinking around MySQL ki how can I implement this thing? And what we exactly tried to do was, we tried to implement key value store on top of MySQL, such that we are able to index data as well. Like for example, the data which we allowed to be stored was JSON, and I should be able to create indexes on nested attributes of it. So we had to implement all of those things, but on top of MySQL, and it was supposed to be sharded. So you should be able to explicitly add more nodes to shards and scale up and scale down both. So that is exactly where I implemented consistent hashing. But at that time I used a library, but I did have, but I didn't know what it was. I just read catch a consistent hashing, something that we used. So I started using it. I was very naive at that time. Then implemented basic sharding logic, hash function on a certain partition. So we were trying to build DynamoDB on top of MySQL. That's exactly what we were trying to. So now that see it in hindsight, I could say that we were exactly trying to build DynamoDB on top of MySQL offering. That's it. And when we were doing that, unfortunately, like I was the only one who was working on it because it was a part-time project. If it works out, it works out well, kind of stuff. And while I was doing that, we were not able to get performance out of it. So then what did we do is we wanted to have a cache for our database such that we don't lose out on the indexes that we need plus the data storage that we have. So the exact schema needs to be there. Like the way we are storing it on our MySQL, so a key value implemented on MySQL, and the indexes that we would want and the caching that we would want on top of the data. There should be no schema difference between the two. Like people should be transparently be able to query the cache and the database seamlessly. So that is where I was like, how do I do this? I need in memory. So I tried implementing it on Redis. I said, I'll write a library because again, a naive approach. I'll write a library that would act as a transformation between the two and all. But then I quickly realized, like I was just going through MySQL documentation and I found that there is an in-memory. So I actually Googled MySQL in-memory cache something. I was expecting to get like caching related information, but then I found the storage engines. And then when I started going through the documentation, I realized that MySQL one of the storage engine is also in-memory storage engine. So what I did was I had one setup for our primary storage. Let's say that's a that's another great design which I was part of. So let's say I had sharded database. Let's say I had 3 sharded MySQL instance, M1, M2, M3. What I wanted was the way I'm storing data in these 3 sharded database, I should be having caches for each one of them. Like the cache C1, cache C2, cache C3. There should be one-to-one mapping between them. So the data of M1 cache, so the data of M1 should be cached in C1, M2 in C2, M3 in C3. Okay, so that the cache of one does not interfere with another, and due to any reason, if my keys overlap, it would still not cause any problem. So that's what I wanted to achieve. But schema had to be same. So schema of my main database and my cache had to be same, which means the way I'm querying. So just imagine that the SQL query, if I fire it on M1, it should give me data from my source of truth. And that same query, I can just tune it and just change it and to point it to my cache. And that same query should work like cache. So basically seamless access between the two. So this is exactly what I did was this was run on top of InnoDB. And this was run top of in-memory storage engine. So I actually implemented key value store on top of this. And now when I did this part, I was able to run that same SQL query. If I run it on M1, I would get it from my database. If I run it on C1, I would get it from my cache. That same query works seamlessly well between the two. And if the data was not there in C1, I can run that exact same query, just pass in a different connection object, and it would just get it from the database. So that was a very nice thing which I discovered at that time. A very obscure problem, but yeah, it at least helped me dive into this part and see how can I leverage this.
The reason for not going for Redis as a cache is basically you want
Yeah,
index
so
only JSON.
so not just JSON, but ability to seamlessly query from the cache and from the database the exact same way. So the SQL query which I was firing, or like for example, the kind of schema I had for my main database was like having one table for like key and then another column like value something, and I would have another secondary table which were like indexes table having like value and suppose key mapping with it, right? So this kind of schema should be like very well present on my cache structure as well. If I would have gone with Redis, then I would have to have 2 plugs. Like I would have to know that if I'm making a query to MySQL or Redis, because the way I would be querying MySQL would be very different than how I would be querying Redis, because we didn't require a lot of fancy data structures given by Redis. We just wanted like get, put, delete. That's all we wanted. But it could be from the database, it could be from the index. And same thing I wanted to be done on database. And actually a lot of things was bogged down by the architect. I had no clue what I was doing. But then the problem, this was the problem which I understood. Okay, we had to do something similar. And at that point of time, I never learned about Dynamo. Although we were on AWS, but I didn't knew about DynamoDB. I didn't knew about this. It was a fancy design that came in, and I, as a fresher, like you just abide to everything that your senior says. Ki, "Chalo, karte to karte." It was all part of that, and I just did this. And then the core requirement was I had to seamlessly query from cache and in memory the same kind of structures and this, so that we can like make just one layer that could basically translate or get put delete through our query to our query engine, which would say, okay, this data is already indexed, fetch it from the index. This data is not in index, fetch it from the main key value store. Something like that. Very obscure design. But yeah, this is how I stumbled upon in-memory MySQL storage engine, and which is exactly where I used it. But yeah, that's also a very fun exercise to do. But this was a great thing where you'd not want to miss out on ability to do complex queries, but still cache it the way you are actually storing it in your SQL storage. You can just spin up another MySQL with the same kind of schema, but just use a different storage engine. That could be a great start for this.
So, I mean, how did the cache get populated? Is it through a replication or is it just
No, basically explicitly
right?
putting it on the cache. Yeah. So the way, so if I'm filing a query onto my main database to get the corresponding key value pair from the index or from this, if it was not there on the cache, that same data was getting stored the same way on the cache. So, there was a lot of like weird things that we did. That's why I'm not basically proud of this, but yeah, something that was like really fun to do. I spent like 3 weeks doing this and it got scrapped and killed, but okay, I got to learn something new. So coming to the next part. So basically the answer to the first one was like just changing the MySQL storage engine. Go through other storage engines as well. Each storage engine tries to make a certain aspect of it very, very efficient. So you might just want to play around with that and like experiment and see if it works for your use case. And it is always fun to go into internals. Chalo. A more interesting part. Implementing word dictionary without using a database. Chalo. Ideas. Did anyone think about it, or let's brainstorm about it right now?
Yeah, I mean, each partition will actually have a sort of sorted keys. That's how I think.
Each partition, but how will you have partitions? How will you represent the data?
As a CSV sort of.
Can we use try, Arpit, here?
Try is in memory, right? But what if your entire dictionary is 1 terabyte big? Right. So you can just try to store the words, and try would only make it efficient to look for words. But let's say if your meanings are too long, how would you store it? Because the first problem that you would have is with try you are making gets efficient or making lookups efficient, but not fetching or basically storing data. But the first problem would be how would you even store the data? Let's say you have 1 terabyte of dictionary to store. How will you store the data at first?
Can we just store as a hash map where we can generate the hash key for
1
the
terabyte big? 1 terabyte big. Will you hash map on disk?
we can store in the file after like memory get increased. We can store in a file system and store in the disk.
But then how will you query? So, but then how does your file look like? You have a text file, let's say. How would your file look like?
Okay, so if we go by sharding way, we can have each file with the naming convention such as A
No,
dot.
no, you are directly jumping to sharding, but you know,
Okay.
you are not allowed to use any database. So it's not MySQL or Mongo or Redis or
No,
any
in
such.
the file system itself.
It's a normal file, like
Yeah.
let's say words.txt. Now in this, what would you have?
Hash for each word, and the value will be the word meaning.
Hash for each word. So
Yeah.
let's say if I have word apple, you would have
I'll get
hash
the
of apple, something,
yeah
and then meaning.
meaning. Yeah.
Okay, and then where would you store the words?
So word will generate the hash, right? So when someone input
But then you need to have the word stored somewhere, no?
yeah, that's true. Can we have other table which have mapping for word and
Word and what?
hash or something?
But hash, so you can anyway compute with word.
Uh,
So would you want to have hash over here? Now again, just put some more thought, Rahul, on this. Would you want to have hash of words over here? What were you trying to gain by doing hashing of word?
the access will be off one, so we can generate the code. It will be like easy access.
It's a file, right? How will you go to that
Hmm.
index? So at least my understanding is, I mean, just store the word and its meaning as a CSV sort of, I mean, key
Huh.
and value,
Hmm.
and keep them sorted. So as it becomes difficult to keep them sorted, so each letter, each word starting with a letter, just keep them in a separate file.
Okay. Ek minute. You went a little far with this. So you have, so the first approach would be to keep all the words like this, and word would be sorted. Correct. And each for every starting character, you might have one file. So let's say a.txt, b.txt, and so on. Correct. Okay. Now how will you query? Now let's say I search for apple
We can do a kind of binary search implementation
in file.
since it's a sorted.
In file.
Hmm.
What if we use an
Prakash
auxiliary?
नहीं कर सकता.
Yeah, Sanjay.
What if we use an auxiliary data structure like a B tree, and the keys of the B tree point to like blocks that store the actual words, right? So a disk block can be of a fixed size, let's say like 5 KB worth of data, whatever, and it stores all the words in that range. And as you need to insert more words, it's like an insertion to the B tree, right? So you just insert that into the B tree, and you just create a new disk block, and then write the data there, and the B tree will point to that block.
Okay.
So, so that way, the B tree is just a metadata, just that it's containing the pointers, and the actual data is being stored on the disk. So that way you can keep adding as many words as you want in these disk blocks. And insertion, querying the B tree is just like a login.
But then where would you store the B tree?
The B tree also will need to be stored on disk. Yeah, the B tree also needs to be stored on disk.
Okay, let's start things one by one. So you said B tree. So let me add a B tree here. B tree mein, what kind of information are you storing? What's the leaf node?
They will be like pointers to the like, for example, every range of like word, just like you said, a.txt, right?
Okay, let's say every
Those
range.
will
So let's say A to B, C to M, N to P, and P to Z, something like this, right?
Yeah.
And then it would point to the actual file or the file block on disk, something.
Correct. Yes. Yeah.
Right. So it would point here, it would point here, it would point here, and you might have the fourth one. The final one points here. Okay, so instead of having one file, you split it into multiple files. Okay. So this way you are gaining on, you can add as many words on the fly, right? And it would basically keep on rebalancing stuff. And the B tree is also stored on disk.
Yes, yes. As a block becomes too crowded, you can just
Hmm.
create a new
Hmm.
range, insert it,
Hmm.
split the B tree there,
Hmm.
and create a new and create a new block. So you can keep creating new blocks on the fly and flood write words there.
Hmm.
If you want to read, you just have to query the B tree,
Hmm.
find out which block it belongs to,
Hmm.
and then maybe within the block you will have to do a linear scan maybe.
Okay.
But the block sizes are anyway constant in size, so that's
Hmm.
usually okay.
Okay. So a great point that was brought is this, the size of file is same as block size. So a quick thing to note here is whenever you are performing any disk IO operation, the unit of operation is same as the block size which is configured. It could be 4 KB, 8 KB, etc. Like you can it depends on the disk configuration that you have. Like what would be the block size? So even if you are reading 1 byte of data from the disk, it would actually read 4 kilobytes of data, and then it would load it in memory, and then you will access that byte from it. Right. So by doing this, so since when you are reading something, let's say the word you're looking for was apple. When you're looking for word apple, you navigated through B plus tree, you came over here. It turns out that it is present in this disk block. When you are reading this disk block, so this entire disk block will be read in memory. And now since it is in memory, even if you do a linear search, that would be still okay. Right. So you can do a linear search within the file block. You can also do a binary search here. No one's stopping you from doing that. Okay. But then always remember the IO operations unit is a block size. So even if you are reading 1 byte, the entire block would be fetched. So this entire block would be fetched in memory. So you can then, when you're trying to access subsequent bytes, you would not know, right? So the thing is, you would not know that this file is already loaded, but you would not know directly, but you would know that this file is loaded in memory. So let's say you accessed a certain byte, and then you are like doing normal file IO and said, give me the next 3 bytes of it. When this call gets translated into the system call, it would say that from this file for this block, I want to read this offset. Then it gets passed to the operating system. Operating system would say ki, array, this file is already, or this file block is already loaded in memory. You can like directly get the data from memory. So then it goes to that particular location in memory where that block is loaded, and it basically accesses that file. It happens seamlessly. So you don't have to change any code. You do the normal file IO the way you are doing, but it makes things very optimal on the operating side. And this is what is leveraging spatial caching. So like, since even if you're reading 1 byte, it is loading the entire block in memory. So if you're very likely to access the next set of, or the next few bytes, like let's say you read a byte, and then if you're more likely to read the subsequent bytes from it, so the subsequent calls become very efficient because because you're not loaded just 1 byte from the disk, but you have loaded the entire block from the list in memory, and this block, and then all the further accesses would happen from memory. Right. So this is a great way. So whenever you're designing, if you're designing any storage engine, you would always have to understand that the file IO always happens on a unit of operation, which is a block size. You have to know what your block size is. So if you're ever building your own database, always keep in mind that this is how your operating system is going to treat every single of your disk IO call. Right? Always remember that. Okay. And within this, once you have the block loaded in memory, you can make either linear search, or if you have binary search, you can do that. But how would you store data in a block?
You would have, I mean, so this would be the word and the meaning, right? So we would have like
Something like
a
this.
fixed, yeah, we'll have to have a fixed record size, and then split the block into those.
Now came the problem. Now problem started popping up. Okay. You said now what you need is you need a fixed record size. Okay. So can you not have a normal CSV as a block?
You mean like variable length, sort of?
Variable length.
You can, but it just One thing is advantage, like, is of course binary search is much easier if you have the fixed record. You can seek to the position immediately. Otherwise,
one way is you can have a pointer which in turn has the data, and the pointer size is fixed, so you can do the binary search.
Nice. Exactly. Matlab, instead of you trying to see or you trying to fix the size of the words and all, can you not just have a pointer? Because pointer is always going to be like 4 bytes or 8 bytes depending on the OS configuration. You would have a pointer of, let's say, 4 bytes long. Like you can have that as a constant, which then points to something and some in-memory structure supporting it. You can do some stuff around that. So just try to put in more thoughts on that side if we can do it. And by the way, B+3 is something that if your dictionary is changing a lot, right, this would be a very good design. Like if you are constantly adding new keys and removing keys from it, this could be a good design, right? But then with B-trees, if you are always serializing the data and storing it, B-tree also needs rebalancing. So you would be always rewriting at least 30% of the chunk of B-tree on disk, or maybe 100% of B-tree on the disk, and then doing file arrangement or disk block or data arrangement here and there. Right? Yeah, Rahul?
So isn't the design a single point of failure because the B-tree is stored in the memory? And if the server crashes, then we'll lose the data and we have to reconstruct.
That is different problem. We are just thinking about like first building it, then we would make it fault tolerant and all of this, those fancy stuff. पहले solve कर लेते हैं इसका. Okay. What if I say that, like how frequently do you think a word dictionary would be changing?
Yearly.
Very, let's say once a quarter, once a month, maybe, right? Because like how frequently a new word is added in the dictionary. Once the dictionary is there, it's there, right? So would you want to have complications like B+3 doing rebalancing every time? Although those might not be called, but with this, what's being happening is you'd have to load B+3 in memory, then iterate through the nodes, find the disk block, go to that block and return the data accordingly, right? Problem number one. Second would be, if my dictionary size is 1 terabyte big, like when would this be the case? When my value or when my meaning is too long, because words are very limited. Let's say only 100K or 200K words are there, but my meaning is too long, right? So then if I'm storing word and the meaning together, then there is a problem, right? Because my disk block size is just 4 KB, and let's say every single meaning that I have for any word is more than 4 MB, then this logic falters. Correct? Then I would have to, identify all the possible disk blocks where meaning would be present and then get the data from it. Because this particularly limits on this thing, right? Because of our disk block size. So you cannot have word and meaning stored together here. You might have word and a pointer to a meaning. So why I'm adding this hypothetical situation of having a 1 terabyte biggest, so that we understand that how, I just wanted to add how can we handle a variable and data or data that could grow very long. So whenever you are designing any kind of storage engine, embedded database or anything, you would always need to think about these factors, like what's going to be the primary use case. Because when designing a system or when designing a storage engine, you would always need to think about the constraints that you'll be imposing on the user. Like you cannot, like if you have seen any database, or rather every single database has some constraints, like your character cannot be more than 256. It basically cannot be more than 256 bytes long. Or if you are having a varchar, it would not store it within the column data, it would allocate a different memory to it, right? Even with respect to embedded databases like LevelDB, or even with DynamoDB as well, the total size of the total size of a document is always a capping limit, that you can at max store a document that is like, let's say 4 MB big. You cannot store a document more than that. Like all of those requirement or all of those constraints that you see is something that the database designer has already put in. Ki, array, this is how my design is going to be. And I'll be imposing all of these constraints just to ensure that I meet my SLAs. Like if I say that I'll serve get in like 2 milliseconds, I should be guaranteeing that. And to do this, I would be having these kind of constraints and I would be playing by these rules. Right? This is where you'd always have to think about the kind of use cases at hand. So in most cases, when you would be designing your own storage engine, you'd always need to consider cases like this. Key, how long would be my key? A great example was that if my key would be of fixed size, let's say with SQL, the old versions of SQL servers had, like if you define a column of size char 8, you can exactly have 8 character long string. So you had to explicitly pad it with like some random string, and then the feature got added where your database could actually pad the keys with like null characters and all. Right. So you would always need to know what's the limitation of, or what's the kind of limitations are you imposing on the user. Right. So given this use case where we are trying to build word dictionary, right? And hypothetically, if my word dictionary is 1 terabyte big, which means that if I have 100K words, the meaning of each word would be variable length and it could go up to 4 MB. Right. So then if you are storing word and the meaning together over here, this block size, this would very easily exceed the block size because only meaning is 4 MB long. So then how would you solve it? You would store the pointer to a separate file where you have the 4 MB of entire data being stored at one place. Correct? So that your lookup is faster. You're able to make good or quick binary search over here and then get the data out of it. Because like you can still fit in like 10, 15 keys within or more than basically 10, 15 keys. You can at least fit in 100, 150 keys within this block. Right? And then have an explicit pointer that points it to its meaning, which is stored at a different place. Clear? Yes, no?
Yes, yes.
Right. So always keep this in mind. The kind of constraints you are playing with, because it would help you make great design decisions. Okay. One final thing before we move forward with this, like, so we understand that, word meaning for our hypothetical situation might not be a great choice. So here, what we would have is we would have word and pointer. This pointer could point into some file where the meaning is stored of the words. It would point over here, something like this. Okay. Yeah, Varun?
When you say pointer, is it file name and the offset, or I mean, what kind of?
You can have it file name and an offset. You can have a separate file name. Let's say each meaning, let's say if every meaning is 4 MB long, so then each meaning could be stored in a separate file. So word and then only a file name. If you are clubbing multiple meanings into one file, you can have a file name and a pointer.
Yeah, I mean, I feel that file name and offset is a good choice because the operating system has the file limit.
It's a good choice. Yeah, Rana?
Arpit, two things. Like initially, when we make a dictionary, like there will be insertion, and then we will choosing the block size as per like the file size as per our block size, so that in memory it can be done. Now, when we let's say next day,
but block size is dependent on operating system. If you have a larger, so if you are managing block size on your own, but if your operating system has a different block size, so then there would be a massive mismatch, because like your one read would be translated into multiple system calls of disk reads.
Right. And then let's say one we have a block size same as operating whatever is fine for operating system. And then so we have, like, I'm talking about insertion. Let's say 100 keys we need to insert, and then we are fixing the length. So we will split this block size again, right? At every insertion.
Yes. So you'd be splitting block into multiple blocks and then splitting it again.
And then like would we, like, let's say there were 2 blocks and it was splitted into 4, and there's a possibility that we can merge into 2. The merging will also happen.
वो तो normal B tree वाला logic है. Merging blocks and all is B tree वाला logic, right?
Okay.
And then the final disk block size would have to go fragmentation and defragmentation, and not merging and all. But if you're doing it, if you're merging, if your leaves are getting merged into one, then you would be doing that basically complete file copy and all, and see if it can be merged.
Okay.
Because at the end, this entire data is residing on the disk, which needs to be there. So if both the size, if let's say you'd want to merge two leaf nodes into one, then you would have to check that the combined file size is less than the basically file block which is configured. Right? बहुत complicated, right? So this is too much. You can obviously design it this way, but this is too neat of a design to be solving a very simple use case like word dictionary. Okay. So now what would be there? Like if we are, so one key highlight here was like using word and a pointer and then storing it here. And this was the outcome of our hypothetical constraint of it having a 1 terabyte big size. Okay. Another thing what you would want to do is here, a great thing that you can do is to a good storage engine always has just one file which is very easily movable across machines. For example, when you dump Redis database, it gets dumped into a single file with extension .rdb, right? So that like you just copy that one file, put it in any machine, and then you can start a database and you'll have everything there. But with this kind of approach that you're picking, with every single thing becoming other file, you're making things heterogeneous. Like you have so many moving parts. Like you'd be, when you're copying your storage engine or your database from one machine to another machine, you would be copying like thousands of files, right? Which might not be an ideal case, right? मतलब फिर बहुत configurations आ जाते हैं. So that is where you would want to come up with a solution where all of this thing is just compressed into one file. Okay, we will go through it. We'll see how we could design it well, right? So it's just a way for me to introduce a few concepts that are very essential when you're designing any storage engines. Right? Sure, we'll jump into it. So features, it has to be infinitely scalable, storage, and API servers. API servers are very easy, scalable enough. You cannot use a traditional database. Words and meanings are updated once a while. Let's say weekly. Once a week, the words and meanings are updated. Lookup, you'll always look up by a single word, and that would be the exact word. But if you want to implement try on top of that, you can do that so that you can have auto completes and all. But that is not big of a problem to solve there. Update is not an entire dictionary, but a change log. So typically how dictionaries are updated is like, let's say you have a dictionary of 100K words. Then if let's say 5 words are added, what you'll get is just those 5 words and meanings of that. You would never get an entirely new dictionary out there, right? And similarly, if some meanings has to be updated, so the changelog would contain the words and the meanings. So if the word is there, you would update the meaning. But if the word is not there, you would add that word in the dictionary. That's what you'd have to do. And the complete dictionary is 1 terabyte big. Now this 1 terabyte big makes like very interesting. Well, it would help us make very interesting design decisions. So we'll start with something that we already know of. What do we know? Like how to scale API servers. We are still not going into internals of it. Like, but the basic thing that we know, like the basic that we know that we can just cut off. We have a user, we have a load balancer, we have multiple API servers. Like this is how our API servers would scale, right? And then this is something that we definitely know, the most basic architecture ever. So request from end user reaches one of our reaches our load balancer, which then forwards to one of the API servers, and that somehow, we will then figure out how that gets it, but it somehow gets the word and then it returns it back to the user. Something that we do, right? And then comes the part that we would be storing the dictionary, where database is definitely we don't want. So what do we have? Like the most common thing that we have with us is like using flat files. If you can use flat files to store data, what better than that, right? So we can do that because it is not a traditional database. And we'll start with the basic one. Let's say, as Varun proposed, that let's just do a normal CSV story like word, comma, meaning in one line. As simple as that. We can have format. So something like this. Let's say A, comma, first letter in the English alphabet. Abandon, ability, able, something like this. You have word, comma, meaning, the way you're storing it. Now, if you store it this way, what if, since you have the dictionary and let's say it is getting weekly updates, which means you can typically copy the dictionary for 1 week across all of your API servers. So what if each API server of yours holds the entire dictionary? Because that's what you want to do, because you are getting like 2 million requests per second for your dictionary app. And when you're getting those many requests, the request might go to any of your API server. And since you're not allowed to use a database as such, so and you have stored it on a flat file as a normal CSV, you can literally copy paste the file, or you can have it configured like all the API servers to have this file loaded or have this file locally present on its disk. This way, what would happen is the request that is coming in, it goes to that API server. API server locally has that file. It reads from that file and serves the meaning. Right. So if we have like each file being stored at for each server, the complete dictionary is 1 terabyte big. So each server would need 1 terabyte of storage. So although our servers were lightweight, but now that 1 terabyte of massive storage is attached to it to hold the dictionary. Now, when we do this thing, there comes in another problem. Like, how will each server get this dictionary data? Not the updates, but the first data that it gets. Right? How will each server then get the updates, that the weekly updates that comes to our dictionary? How does each server get notified here new updates are here? Like, how would it pull the data? What would it do? Rolling update? Like, there is so many questions out there. If there are 2000 servers, like since we are infinitely scalable, let's say we want to have 2000 API servers that serve our dictionary app. If there are 2000 servers, then to serve 1 terabyte of dictionary, we are actually having 2000 terabytes of storage, where like each server is having its own set of read-only dictionary. Like this is, this is astounding. This is something that is is out there leaking money, and you can actually feel it. Yeah, this is 100% waste of resources that we have. Right? All of this is a very hypothetical situation, but like you can understand how grave the situation could get. Right? So what does this mean is since we definitely know that we are leaking storage space, because like just to serve 1 terabyte of dictionary, we are using 2000 terabyte of storage. How about we store this dictionary on a central location, right? What central location? If we cannot use a database, it could be like flat file is nothing but a blob storage, and why not just store it on S3, right? S3 could be replaced with any network attached file system, anything that would, like, a lot of your machines should be able to seamlessly access that same data, and you can have it read only, because updates are just weekly. So you can fairly assume that that data is mostly read only, and no one is going to perform writes anywhere on that dictionary. So your server having that data, so now you see your server is still having 1 terabyte of storage, but to get the dictionary of data, it would make a call to S3, because S3 is that one place from which it would get the data, and it would store it locally and then serve it. But every time you cannot copy the entire dictionary from S3 and store it locally. There are massive problems, lot of network IO there. So that is where what do we do is somehow our server directly talking to S3 and getting the word and the meanings. Right? Somehow if we can directly do this, like something like a network attached storage. So this S3, although I've written S3, you can assume anything which is a network attached storage. This could like do a great job. Okay. Any idea how we can do this part? If our server can directly talk to S3 and get the word and the meaning, can we directly do that? S3 or any network attached storage, you can assume just a disk is connected to a network. How can we efficiently query a disk to get a data? So given a word, give me the meaning. Any suggestions here?
And you can store every word as a file, and then you can just
great hack. Good thing that, so if you had like very few words, so yeah, you can definitely do that. But yeah, a very nice solution, a good one in most cases. Like just store each word as a separate file, as simple as that. So you go to that place. So let's say someone word search for apple, you go to the dictionary, it is stored in a certain path, you just open apple.txt, it would have its meaning, and you serve it back. Right? So all the machines of yours hit that common place. So the one way to implement it on S3 is on S3, create a bucket, within that create a folder. In that folder, one file for each word. You directly make a call to S3. to get that file. And once you get the file, so file contains the meaning and you serve the meaning directly. Yeah, Anshul?
We can store it in the form of like something like tries. Like if we want to search
APP, मतलब every character becoming a subfolder.
folders. Yeah.
You can do that. So another great approach would be to like have one, like the way you'd be storing is like A, then a subfolder P, then another subfolder P, then subfolder L, then subfolder E, and then within that apple.txt.
Right.
So this kind of approach also works well, but this defeats the only thing that we are like, our database needs to be shippable. It should be very easily copyable if you would want to do that. Right? A nice solution, but a good one. A lot of real world systems actually exploit this behavior very well to make their reads faster. Right? So it's not something that could be totally discarded, but a good solution. What if I just have one file? Can I like do a pointed query? Like, because if you see, this is exactly what we want to do. Let's say you just have one gigantic 1 terabyte long file having all the words and its meaning. Right. So if you think about it, when I'm querying for a word, what I am really doing is if this was a traditional database, I would be running like select star from words where word is equal to apple. It would go to that corresponding row and then get the data. This is nothing but a pointed query. You exactly know what you are looking for. So this kind of behavior is something that if we cannot use a traditional database, we would have to mimic this behavior. This is a good hint. Think about it. Can we do pointed query somehow on just one flat file, one big gigantic flat file?
We have to get the offset in the file, but how do we
correct.
get the offset?
Correct. On the right track. On the right track. You would need an offset. So a great start is if you'd want to do a pointed query on a file, recall on every file IO, you can do a disk seek to a certain location in a file. And from that offset, you can specify how many bytes do I want to read. Right. So somehow you need to find like this word is present in this offset in the file. If you have that information, you can do pointed queries. How will you get that? How does database get it? Let's say if I replace S3 with MySQL, how does MySQL internally do this?
Can we order the data in that file?
We have data ordered. We have everything is sorted by words. So word comma meaning, and the words are this combination is sorted by words.
Arpit, can we do like this? Like, let's say we have a word A, B, C, like A, like, and we know this is 2 characters, and then multiply by bytes, and then we calculate what will be the location.
How come? Because there is also meaning stored there, na? And the length of meaning could be variable. Like A ka meaning could be just 5 character long. A ka meaning is like 5 MB. Because you have word comma meaning, na? That's how we decided to store it. The normal CSV like this. Something like this, right? A comma first letter in English alphabet. This is what our words or TXT looks like.
We can store starting and ending words for each of the blocks in memory.
And there are no blocks. There is just one file. This one file just.
Yeah, but we can store it in memory, and we can find in which block it can be there. Like,
so then you'll be reading that entire block in memory.
Yeah, that particular block in which.
But block kitna bada hoga? How big would your block be?
We can keep it customized, like 5 MB, 10 MB, or something like that.
But then every time for even a word, you would be reading 5 MB long data. Like unnecessary reads, na? See, you all are, by the way, great thing, you all are converging to the right answer. You all are converging to it. I'm so happy. Like, yeah, Anshuman?
So can we do a buffered read of the file? Don't read the file at once. Like read it in a buffer, part by part. And once when you read a buffer, read the last word in that buffer. and from there you will get to know if your word should be inside this buffer or not.
And then, so this is like, so this is like a linear scan.
Right, but
you have word comma meaning. Now you would not want to read meaning because like that's of no use.
The words, yeah, I mean the files that you load in buffer, they will be order of 1. I mean, if they don't exist, and only the yeah, it would be linear, but
it doesn't add up. You guys are really doing a fab job here.
Arpit, like basically the problem we are solving is the metadata that we want, and then while inserting, can't we store the information about how much character the meaning is? And
why not? Why not? Right? We can, because what I gave it as a hint, like how is MySQL doing it? If this was not a flat file, how does MySQL do it? MySQL has an index to support, right? So what if you create an index out of your dictionary of all the words that you have? What if you create an index? Okay, we will come to it. So S3 is not a database. We cannot make pointed queries, but we need support of pointed queries. So how do we do this? So just like any other network attached storage, S3, like pick anything. So here I'm just using S3 as a word. This applies to any network attached storage, any disk read, anything. So every single blob storage is, be it disk buffered or cloud based, it supports byte range features. So similar to how you can read a certain range of data from a file, you can do it from S3 or any network attached storage as well, like something like this. So from this file on S3, don't give me entire file. Give me all the bytes data from offset A to offset B. It would just read that chunk of data and stream it back to you. This is exactly how your normal file protocol also does it. Like you can open a file, read from a start offset to an end offset, any offset that you pick, like let's say 100 to 200, it would give you that 100 bytes worth of data. Right, so this is something that is supported by every single storages, like be it file storage or cloud storage. You can leverage this very well because this is what is giving you ability to make pointed queries. Right now, all we have to do is just leverage this to make our things better. So similar to what MySQL does, what if we do this? What if we know the start and the end offset of each word and its meaning in the dictionary file? Let's say you have a massive file words.txt, and what do we have? We store this information. The word A starts from 0 and has length 127. So this is 0 and this is 127 characters. My word abandon starts at offset 127, which is this, and has 130 length, which is this. Then my word ability starts at 257, which is this, and has a length of 100, which is this. Right. So this, what you are doing is, what you essentially wanted was something like an index in MySQL. If you don't have indexes on flat file, you create one to help you build, to help you make pointed queries. Because now if you see, this file is for now, let's store it as a separate S3 file. Let's say you have this file called index.txt, right? And you read this index.txt file, and from this file, let's say you make a worst case, you make a linear scan on this file, but this file is not as big as your 1 terabyte big file as like your dictionary file, because all it contains is one word, 2 integers, and 2 separators. That's all it contains. Right. So what you can actually leverage over here is, like, let's say you make a linear scan on this file. We'll see how big this file would be here only. Okay. So when we are doing this, we store it as a separate file called index.dat. So now let's see what is the size of this index.dat file. I said the entire size of dictionary is what? 1 terabyte. So these calculations become very important because your use case or your design would be very dependent on that. Right. So these are back of the envelope calculations that we have to do when we design any system. So let's say if you want to measure how big our index.dat file would be. So the total number of words in dictionary is 171K, close to 200K words are there. So we said that the length of one entry, which is like one entry, this is nothing but average word length plus two separators and a new line. Let's say this is how this is exactly how we store the data. So two separators and a new line. Like so, average word length plus 3 plus 2 into 4. So basically 2 integers we are storing. They will take up 4 bytes each, right? Although it looks like characters 1 to 7, but you can like marshalize it as an integer and write it in 4 bytes, right? So you are using marshalling techniques to like store just integers in 4 bytes. So the average length of one entry would be 15.7 bytes only. 15.7 bytes multiplied by 171k words turns out to be just 2.6 MB. That is it, right? So a massive looking dictionary, which was 1 terabyte big, was like basically think of it like kind of encyclopedia, right? So this was like this massive encyclopedia that you had, where each word was like so it only has 171k words, but the elaboration of it is like humongous, like बहुत कुछ लिखा about that word, which is why the meaning is becoming too long, but the word is or the number of words that you have are too short, right? So whenever you're designing something like that, always think what are the constants that I'm playing. Just do a basic back of the envelope calculation, and you see that 1 terabyte long dictionary got compressed, or the index of that with just words and offset is just 2.6 MB long. Now this 2.6 MB is something that you can like, you can just store locally. Like instead of having like 1 terabyte big storage, you are just having like, oh, it's 2.6, it's not 26, it's 2.6. Acha, dot hai. So here what you would have is you can just load 2.6 MB of index file in memory. So now the flow would be your API server. Let's say you somehow have, we will also make this thing better. Let's say you somehow have this index.dat file. So now your server, instead of downloading that 1 terabyte dictionary file locally, it would just download this another index.dat file from S3. Now this index.dat file is something that it would store locally, and your server can keep 2.6 MB is nothing to be kept in memory. You can very easily keep it in memory. So you can keep 2.6, you can load this data in memory, and whenever you are firing a query against a word, what you'll get is you'll get the starting offset and the length, how long is the meaning. So from this you'll fire S3 to make that, that call of that byte range. From this offset of this length, give me all the data, and which would give you the meaning of the data. So when your server starts, you load the index.dat file from S3. You load this index file in an in-memory hash table dictionary. When you receive a query for a word, you check the dictionary for the existence of the word. Locally, you have the index file already. If it does not exist, you directly return 404. But if it exists, you get the start offset and the length. You make a call to S3, get the data from that byte range, and you return it to the user. Okay. Any questions? So a key point to note here is something that our traditional databases would have given us was indexing by default. We implemented indexing ourselves, right? And if you see, this was like 1 terabyte to 2.6 MB. It's like very skewed right now. But in most cases, the indexes that you have for any databases, they're equally leaner. That's why, as I said, like in past weeks, that if you want to have great performance of your out of your database, just ensure that your database can keep all of the indexes in memory. That's when your database would have a great performance. You can reap out a great performance out of your database. This is exactly why, because your indexes would be too small as compared to the data that you would have that you're storing it in your database. Okay, so this was about like get and query, the way we addressed it. Like this solves a nice bit of problem. But now what comes in? Now comes the question of updates. Like when we kept it, like updates to dictionaries are obviously not that frequent, which means that weekly we might get a change log where you would get word and the meaning as part of change logs. Like whatever is changed, you'd get it. Either new word added, existing word deleted, or word modified, something like that, you'll get it as a change log. So what you can do is, if you keep your main dictionary sorted, if you sort the change log, you can apply the merge sort wala logic, the merge sort wala logic. Since both the lists are sorted, you can just create a third file by iterating over this two. Like, so sort the change log, pull the already sorted dictionary from S3. So this could happen just once on a separate API server. You don't really have to do it on all the servers that you have. You can just do it once at one API server level, and then you are done here. Right, so you can do it and then re-upload it to S3. So updating the index.dat file and updating the main dictionary file. Right, so merge the two sorted list. When conflict takes, you take the entry from the changelog and then you move the pointers forward. A very simple strategy to merge the two sorted lists, and then you upload the merged dictionary to S3 and you upload the index file to S3. Right, so this way you solve the problem. So this is a crude example of it. Like, how would you do it? So let's say your dictionary was A and A dash is the meaning, B dash is the meaning, C dash is the meaning, and your changelog says C ka C double dash hua and F ka F double dash hua. So the way you do it is you'd iterate dictionary word by word, and you'd say A and C pe pointer hai, C is greater than A, so I'll write A into this new file. Then I'll go to B is less than C, I'll write B into the new file, and then I come to C. I see my changelog also as C. So I'll pick the entry from the changelog and write it, and then increment both the pointers. So my second pointer will point to F, while my first one went to D. So D write hua, E write hua, then F ke case mein it would write from the changelog, and then it would continue this. That's a normal merging of two sorted lists. This is how we would go for this. So the entire process is just order n. So just rewriting entire dictionary once and then uploading it to S3. So a separate process that would be done asynchronously. Right. So now comes a few interesting challenges when we do this part. Right. If you upload the dictionary and the index to the same location, as in the same old location on S3, because on S3 you had two paths, one for your words.txt, the other one for your index.dat file. What would happen here if you have this kind of thing? Although the answer is right there, but yeah.
Like you will, like one TB file will get accumulated and the size storage will increase.
No,
Like
why? Because you're replacing the 1 terabyte file on S3. You're replacing the 1 terabyte file on S3, na? So accumulate kahan hoga?
Okay, like it's
The
a append,
index
not
is
on
gone
append.
now, so you may have to update the index as well.
Right, because what happened was, when you did this merging of dictionary and the change log, and when you're writing it, right, so the dictionary got updated, and while doing this, you are also updating the index.dat file, right? So you are uploading the new dictionary and the new index.dat file. But what happened with our architecture is the index is loaded in memory over here. So your API servers are already have loaded the index.dat file, the old index.dat file in memory, and they're serving it. And then you suddenly change the main index, the main dictionary file. Now you'd still get the word, you'd get some offset like start and length. You would go to that part, but now that part could point to some other word altogether, some garbage altogether. Right. So this is where this new challenge would come in, where your servers have the index file built for old dictionary, but we have updated the dictionary file with the new content. So when we would be making get queries over here, we would be getting old and garbage data or incorrect content to the users. Right. So this, although looks a very simple solution, but would cause a mayhem if you like directly update the source data. Right. So again, the problem comes on, like, how do we notify servers about this change? Because now servers have to be notified here, in the dictionary got changed, the index file is updated. So go ahead and load the new index file from the memory. Correct. This is the new problem that would come in. Like how, like we would have to tell our servers to go ahead and load it. So how do we ensure that this transition happens smoothly? Any approaches that you guys have in mind? How can we ensure transition?
So dictionary, yeah.
Okay, so I mean that's it. There is a data slash dictionary.csv and there is index slash. I mean, along with it, you just save a epoch, and I mean you save the same epoch for both of them, and it's like one-to-one mapping for them. So, I mean, and whenever server starts and tries to load the index.dat file, it'll get the latest dat file and maybe it'll update every week.
Correct. Matlab, a good start using epochs or using some. So instead of replacing, so what you're primarily proposing is instead of replacing it, you create another file.
Yes.
Right. Yeah, Sanjit, you had something.
Yeah, just building on that. That should be a unique tuple. The index.
That should be unique tuple. Exactly.
Tuple. And you can either, when the API server gets an update, he can either notify the other servers, or he can update a central location which other servers poll. And we should keep track of once when nobody else refers to the old location, then we can auto purge that from the S3 storage. So when when everyone has updated to do the new location, then it's safe to go and gracefully delete
delete the old one. This way we would save our storage. Nice. So we would just see these approaches formally now. So there is just one more caveat which I would like to cover that. So since your API servers are auto scaled, you don't have a fixed inventory. You can just have a thread. Like typically that's how it happens. Like you just make one call every 5 minutes to see if index.dat changed. If it changed, then you load the new index.dat file, update it. But obviously if you do it every 5 minutes and if index.dat file changed in the first minute, then for 4 minutes you are serving wrong data. Obviously that is not a good solution. So you pull a meta file which suggests. Then another approach could be like somehow your API servers know that something changed, right? So one way to do it is like instead of loading index.dat file, like let's say you have another meta file whose job is to like parallel path. Okay. So you have another meta file which suggests the last changed time, and through this you can get like, okay, your API servers would know that my file got it. Like basically implementing this very approach. Like how can you implement it? You can either have a separate file which says that something changed, that all of your API servers are polling in a thread, or what you can do is you can use the file object properties, like updated at might change, or the modified it property of a file which is there gets changed. You can leverage that to see if something changed. But obviously this has its limitation, because for this duration you would still be serving wrong data. So you have just tried to minimize the scope but not eradicate the problem. Another solution which right now has been proposed by Joybo, Varun and Sanjit was like about not replacing the file but having a parallel setup. So no polling, no in-place update to dictionary file or index file, but you would upload the files to a new location, which means your meta file that you might have would have the index file and the data file. So what Varun suggested was to add a epoch to it, like some sort of unique. So the unique identifier, like doing it this way, like you have your index.0.dat file and dictionary.0.dat file. So this D00 would see that, okay, my index file is index.0.dat. So I would have to make query to dict.0.dat file. Right. So having some sort of this, or to make it convention over configuration, configuration over convention, your meta file could have like index path and data path, and your API servers would load this at the start. Now what would happen here is once your application server reads the file, it reads this file during the boot, it would read, let's say it's P11 and P12, the old path for index file and data path. So this path are there on S3. When your application server will load this file just once during the boot. Now, upon changes, these paths are updated. Let's say your job ran, your weekly job ran, and these paths got updated to P21 and P22. Now, new servers that would come up, since this update has gone to that same meta file. So meta file constant, or a meta file is same path, like /meta.json file. right? So every server that boots up hits this path meta.json file and loads the index file and the data path from S3 and then basically uses it to query it. Now, if this path got changed, what would if this path got changed means this same file got updated, right? So you are having separate files for index and dictionary, but the meta file would be updated or it would always be replaced whenever your job would run. So new servers that would spin up would all load the new path, which is new servers would load P21 and P22. The old servers will still continue to serve data from P11 and P12, right? Which means that I'm not seeing any garbage value served to the user. Like my user would have no impact whatsoever. They might get stale data, but they would never get wrong data, right? So this is very important. So I'm just trying to slowly transition it into like a seamless process. So loading it. So new servers ka problem is solved. Old servers will continue to serve from old index path and old data path. So instead of having one copy, we are having two copies now, old and new. And then we can slowly, once we know that our process is done and the new path is updated, we can then slowly start terminating the old servers or either do and reboot, whatever works. So let's say we just terminate the old servers so that new servers that they come up, they would load the file meta.json and they would find a new paths here. Right. So this is typically rolling upgrade. So you have rolled out changes and then you are then slowly deleting your old infrastructure and the new infrastructure that comes up with the newer change. This is typically how most of the deployments actually happen, rolling upgrade. So you pull the server out of your load balancer and then or rather you basically delete a server. When your auto scaling says the array one server is deleted, it would add one more server to it. And when this server is starting, it starts with the newer configuration or the newer code base. Like this is exactly like that. Okay, so now you are slowly replacing your old servers with the new servers. So gracefully, you are doing this seamless transition from old to new. And once all of your servers are replaced, you can delete the old dictionary and the old index because it would never be queried. Clear? Right. So now comes the next part, like being greedy. Like we already had index.dat file to be like just 2.6 MB. Can we make it smaller? So here, this topic I specifically want to cover is whenever you're designing any database or any storage engine like this, any embedded databases like this, you would have to consider about every single byte of data that you are like that you are putting in. For example, this separators. Do you need separators? Like how can we make this smaller? We are using 3 separators like colon, 2 colons and 1 new line. But do we really need that? Like you can have something like this. So we use 2 colons here, 2 integers. But since integers are fixed with like 4 bytes and 4 bytes, I can just have something like this. I can just get rid of one of the separator. I can just have word, one separator. And then because since my word is a variable length, I don't know when my word ends. Right. So then I'd have one separator and then I have 2 fixed bytes or 2 fixed 4 bytes. So I just saved 2. So I just saved one separator here. So 2 bytes for 2 or 2 4 bytes for 2 integers that I have. So another way to do is key compression. So if we can apply Huffman compression on all the words, like for all the A to Z words that you have in your dictionary, if you apply Huffman compression, you can save about 40% of your string. So these words like abandon, this could be like basically compressed by 40%. So if you do this, you can typically make your index.dat file just 2.1 MB. Like 2.1 MB might seem too small, but if you're not implementing a dictionary and if you're implementing a key value embedded DB like a level DB or a rocks DB, this would be a game changer. Like if you're compressing the data and storing it, most of the embedded databases like level DB, rocks DB, all of these databases do compression to save space because our embedded databases have to be like very tiny to be like moved here and there. So with dictionary example, this seems too small, but at scale, this becomes a game changer. When you have like a millions of keys, this becomes a game changer. Like abhi to 100K hai, when it becomes million, then it like hundreds of MBs ka storage space saved on just keys ka data that you have. Okay, so compression is very important. Now addressing the big fish. that instead of having two separate files, like obviously that was the whole point. Like, why do we want to have two separate files? We can just, how about unifying them so that we can easily ship our embedded, our database from one machine to another machine if required, right? So how can we do this? This is something that is a very basic thing that we all have studied in our computer networks. Like you can merge your index and data, but then you need some way, like how about just copying like index file and then data file, right? So index file, so your data file is a dictionary and the index file is something that we discuss, like index.dat file. You can just merge them at one, but you need to identify when your index file completes and when your data file starts, right? So to do this, we need a separator, but your separator is definitely not a good choice. So a better approach here is to add a fixed header which stores some basic information about your database. Let's say when you add a classical header at the beginning of it, it would have information like how many words are there in just one 4-byte space. It would have the byte offset of this separation. So the place from where the data file starts and where the index file ends. So that one offset in this file where this happens. So this means that whenever you are loading something, you would first load the header. So this header is typically like your central meta.json file, which has some basic meta information. So you'll load this thing. From this, you'll get the offset of where the index file ends. So you will read the index. Your API server will read this index chunk from this one common file and load it in memory, and then continuously start serving the request here. Right. So this kind of approach is very common when you are designing any kind of embedded data with any kind of storage engine like this. So having a fixed size, and obviously this header cannot be a variable length. Every header in every single protocol is of fixed size. If it has variable part, it is also specified ki what's the length of it. So it has to be very predictable. Every single information has to be self-contained. So having a fixed size header which stores information like offset of index and length of the index, like from what position does the index starts, what's the length of the index, offset of the data. So from what offset does the data starts, and some meta information like total keys or total words, what's the version, like let's say when you are last updated at or something like that. All of that information will be stored here in this header. So when your application server now boots up, what it would do is from this one file on S3, instead of having two files, we're just having one file. And from this one file of S3, it would first read the header. From the header, it would get information from this offset to this offset is my index. So it would read that same offset as part of index, load it in memory and start serving the request. Okay, so we have to define, when we're defining our own storage engine, we have to define our own header protocol. Right. So what kind of information would we want in a header? Right. And it is up to us to decide it. So any question around this design?
Arpit, in this, like we are storing two integers. Like, can you go back to previous one when we are storing the indexes? Yeah.
Okay.
So if you're storing A is varying from 0 to 127, abandoned to 127 to, let's say, 257, right? So can't we just store 127, 257, and then like length we can reduce by to -1, like?
Okay. What would happen if you do that? Because the kind of information that you have would be, if you're not doing any post processing, I'm assuming you're not doing any, once you're loaded to index, are you doing some post processing on that?
No.
No, right? Okay. So when you are just giving the start offset there.
End
right?
offset.
End offset of what?
Like
of the
let's
word.
say abandon, I will store 257.
You'll store the end offset of it, but then
Yes.
from what position does abandon starts?
So we can store that in header, like
For
let's
every
say
word where it starts.
No. So let's say A we store 127, abandon we store 257. So we can just like if we are searching for abandon, we can just do like what was the, like, since it is sorted, like 257 minus what was the length of the previous one.
Correct. So there exactly. So you are using information of in that list uske upar ke ek word ka information.
But anyway, we are going or like when we are doing binary search, like
Yes,
it will be just -1.
I'm not saying no to that. I'm not saying no to that. I'm definitely not saying no to that. You can do that. It is your protocol, right? You can do that. The reason why I chose to go with this approach, it might not be like as optimal with space as possible. But in most cases, this kind of protocol is typically abstracted. You would always have this start and end being stored in one place, like start or length, right? So that you can like have it distributed across. Like information is self-contained. You don't have to take help of one entry above and one entry below to make anything, right?
Right.
But your approach is correct. You can do that. You can very well save 4 bytes of more information from that.
Right, like I was just I just asked because like anyway we are reducing down the MB from
can do that.
2.6 to 2.1, so that's why.
Yeah, you can definitely do that. See, it is
I
up to
think we
you.
can't use, sorry, yeah, we can't use the hash map data structure if we are doing that. Maybe that's one reason.
एक reason ऊपर जाना पड़ेगा उसमें.
Hash map.
That's actually a great point, Varun. Thanks for bringing it up. Because if it's a hash map, how would you know which word is like just above it?
Yeah, in hash map we won't. Then we have,
If it's a list and then you're doing a binary search, then you can do that.
yeah.
This is also the design that's used very similar for zip files on disk.
Zip files, yeah. Right. So now this, so the main reason why I wanted to cover this, although this seems like a very trivial thing, but it has a lot of building blocks for a lot of the systems out there. Like if you are reading about file compressions, if you're reading about file formats, JPG and other formats, if you're building or if you're playing around with LevelDB internals, RocksDB, or if you're even diving into HDFS, Sabka foundation is this. Matlab, once you know the trade-offs we made and the way we evolved our design, you would be able to comprehend any such design like HDFS ho gaya, Google file system, or even a Spanner internals also uses something similar to this. You can go through React, Bitcast. Sabka foundation is exactly this. The way we have evolved this system and how do we do that. And again, something not hypothetical. I exactly designed this very database of something very similar design at Amazon. It was called as RODB, read only database. They can't come up with a better name there. So they use it. We used very heavily one embedded database. We defined our own header protocol. The way we were storing the data. Each file was 15 GB big, and we used to exactly make query this way. So we used to load index in memory. We used to first load header, then load index, and we would build an in-memory hash map of all the keys that are part of it. Request came in, we used to directly we used to from the in-memory loaded index, we used to get the start and the end of set. We would go to that place and get the data and then return it to the user. That's exactly what our design was. So this would definitely come in very handy when you are basically playing around with embedded databases, especially or when you're designing your own protocol, something like this. And we would come into the cases where this would come in very handy with real world examples. Nice. Second cohort where this was covered in 30 minutes, 35 minutes. That's it. ये बार मस्त लंबा चला, 1.5 hours. Nice. But we went in a very nice depth. I'm happy for that. Chalo. Will any question before you go on a quick break? Right? Chalo. Let's take a quick break till 5:35, and then we'll come back and we'll go into block structured storage. We'll again build a key value store. The reason I'm like so picky on key value store because like key value store lays a foundation of all the data. You can build any database if you can build a key value store on that. So it is simple to comprehend, and you can obviously extend the design to any kind of system that you would want. Right. So we'll talk about log structured, really fast key value store and how do we design that. If you're unfamiliar about log structured, don't worry, we'll cover log structured as well. But you can obviously Google in your time. Yeah. Chalo. See you at 5:35. Thanks. Nice. Sure. Next comes the part of log structured storages. Log structured storages are like really insane. They work on a very so they make a lot of sense. They are very intuitive. The kind of design that log structured storages are built on, they're very interesting. You would see ki, "Arey yaar, this is how everything should be built," but a little counterintuitive as well. So when I was first introduced to this part, I was like, "Ki, matlab, why would you want to do that?" But when I actually ran the benchmarks, I actually found that it is so beneficial for us to like try to build any system around log structure. It works wonders, and you get some great performance out of it. So, how many of you are aware of log structured storages? Varun? Can you explain it in like few sentences?
I mean, you just store the data as a log sort of thing instead of storing complex data structures like B-tree. Just store it as a flat file and build on top of that.
So that's exactly how I would have said like complex data structures like B-tree. Like even with the dictionary ka example, we saw like we tried to make it complicated using B plus trees and nodes and whatnot. But what log structured says is log structured. So name might be a little weird, but basically that's what the operational name is. So it's like structuring like logs. Like just assume that you have opened the file in append only mode. That's what the criteria is. Like you cannot go back, or you can do you cannot do a disk seek and update it any other place. All you can do is just insert and make new entries. That's all you can do. Right? And that's what the log structured storages typically looks like. So what we'll do is we'll try to build a key value store using log structured. So log structured storages in general, it's like anything that you do or any file you open will always be open in append only mode. The writes has to be sequential. So you cannot make any updates to existing entries on the file. So which means no disk seeks are allowed when you're writing. When you're reading, you may want to do a disk seek and read it. But for writing, you are not allowed to do disk seeks. So it's like basically how our log files are created out of like any of our existing system, like Nginx log files or GUnicon log files. It's exactly that. So why are they beneficial? So you might not see a massive advantage of log structured file if you're using an SSD. But when you use a spinning disk hard disk or a classical magnetic hard disk, where there is this actual head movement of your head of your disk to read that particular sector, that's where this comes in very handy. Because since it is just sequential, the head of the disk does not have to move basically back and forth to read and write and do the to write and to do update here and there. So it is always moving like a very little bit in one direction. So why disk seeks? Because disk seeks is something which is the most expensive part when you're doing a disk IO. With magnetic storages, with basically spinning disk hard disk. Right, that's where it is the most expensive part. So log structured storages leverages that. Now you would say, "Arey, abhi to SSD hai, then why are we even worrying about that?" Most of our infrastructure would be running on top of magnetic disk. You are using magnetic disk to save cost because SSDs are costless compared to spinning disk hard disk. So when you are building a storage engine at scale, where you say you are ingesting petabytes worth of data every day, you cannot afford to host that data on SSD. You'll use it a cheaper storage like magnetic disk. Right? So you'd always need to understand when will you make such decisions and why. So people use log structured storages for high write throughputs. Like even on spinning magnetic disk, you'd get high write throughput because there is no time wastage for disk head to move. It's always write. So whenever you are having a very high write throughput, like a classical example would be Kafka or your event bus. When you are ingesting a lot of streams or a lot of messages onto it, I've not gone through the internals of it, but there's a very high possibility it might be using something like this. So, to just register entries about it. about the new events that are coming in for a topic. So if any one of you would want to dive deep and just help us understand if it actually does that, that would be awesome.
Yeah, it does that.
It does, right?
Yeah.
Right. Yeah. Basically, that was my best case. So that's how you get a very high write throughput on any system. And another place where you would see similar thing is when you have something like commit logs or your bin log files of your MySQL when you're doing data replication. All of those things are also like it never goes back in time and updates. So the file is always open in append only mode. So a great advantage of having append only storages is like you get chronology by default, because like since you cannot go back in time, the new entry that you make will always be like matlab, if let's say you have a variable a whose value got changed from 1 to 2 to 3, you would get 3 entries there, a equal to 1, then a equal to 2, then a equal to 3. So you get chronology by default. So you can easily, if you want to, you can actually trace back and see the older value. So you can actually theoretically build a time travel out of this for variable values, how it got changed through this system. So such storages does not give a great performance on flash storages, as I mentioned, because there is no disk seek happening, but still cost bach jata hai. So if you would want to build a key value store on a log structure data, the biggest constraint that we have is like, get is still okay, we'll figure something out. Put is okay, we are just doing append only, so let's just continue writing. But you cannot, when you're doing put, you cannot do an update, like because you're only doing append. So what would you do? So let's say get key would return the value of key from your log structured system. Put key would either create or replace the value, delete key would delete it, right? So similar to dictionary, a very simple design of this would be like a single file holding all key value pairs. So as and when it gets like any put request, let's say it gets put of K1 V1. So if it gets puts of K1 V1, it wrote here, and then it got put of K2 V2, it wrote to the next line. It got K3 VT, wrote to the next line, the next line, the next line. Right. So it gets a very high throughput because typically that's how typically that's what you have when you are opening a file in append only mode. That's exactly what you are doing. But when you are doing a get, let's say if someone asks you to give me key K3, you would have to start something from the beginning and then go next line, next line, next line, and see, array, this is K3, now I'll return. But then you don't have to, you cannot stop here because K3 could have been updated niche as well. So you would have to go through the entire file and get the latest value of K3 and then return it. So your get of a certain key becomes order n. Your put is order 1 because it is just appending into the file. Your get is order n. Delete to abhi pata hi nahi hai how would we implement it, because that's a very far-fetched thing. But pehle get put, let's solve. Right. So first, but let's see how we can implement delete. Right. So we know that put is just an append operation. So it would add one more line to it. So similarly, delete can also be a put with a new entry. Like let's say you, for every entry that you write like key value, you also have a is deleted something that we borrowed from MySQL, right? So if it is true, then we would say the key is deleted. So when you are doing get, you are iterating through the entire file, and if the last entry you get for a key is deleted true, you would say that key does not exist, right? But the entry would still exist in the file because you are not going back in the file and deleting stuff from it. So, but instead of doing that, of having a special value, because the problem with that would be like your deletes are not that frequent, but you would be for every write that you are doing, if you're having this is deleted, you are just wasting 1 byte of space for all of those things because your deleted is just happening like once for a certain key. So a better approach can be delete can be a put with a special value. So let's say -1, like typically how we used to write our C code, when we return -1 for a certain error condition, is something like that. Let's say -1 as a value could imply delete. So you can use any magic number that you would want that is excluded from your use case, some special garbage that would denote delete. So this way your delete also becomes order 1 because your delete is also just a put with a special value. But now again, while doing get, you'd have to go through the entire file and find the latest entry and see if it is a special value, then it is deleted. If it is not, then you return the value. And if you, after going through the entire file, you don't find a value, matlab key does not exist, right? So each, okay, that's fine. Each value would look like key comma value. So do we know in one entry, like when we're designing this, like, so, you know, our key length could be variable, our value could be variable, like the length could be variable. With this, what happens is, since lengths are arbitrary, we have to store key size and value. Something that we were discussing with word dictionary as well. Like, you know, we don't know how big of a key length it is. So when we are registering an entry in the database, or when we are implementing a storage, we would also need to know we were just, up till now, we were just storing key and value, but we would also need to know, like, what's the key size, like how long is the key, and what's the value size, means how long is the value. So that when you're reading the entry, you would read these some information which I'll cover later, and then you'll read 4 bytes to get the key size, then 4 bytes to get the value size. Then this key size, this 4 bytes mein, the whatever value would be, that would be the number of bytes jitni badi key hai, and then the number of the value within this would be the byte length of how long the value is. So you'll read that much of bytes, that would be your value. Right, and this is how you would identify, okay, this is my key, this is my value. Right, so that is why you would need key size and value size to be there. Now, this is the most interesting part, like crashes. Because when we are writing, and this is not just specific to this block structure, this crashes is something that we can think about at all possible cases, like every single system that we have designed. Just think about when anything would crash. Like, what if while creating an entry in the file, although it just append only, what if our machine crashed? What if our data is partially written and your machine crashed? Like, your data is written till this, and then your machine crashed. If your machine crashed, what would happen is, if your machine, so since a machine can crash anytime, you would have to have a way through which you can find out if you have a partially written entry. How will you do that? CRC, right? Something that would help you detect errors, right? So a great way to detect errors is using CRC. So apart from the key size, value size, key value that we had, we would also add a CRC at first, which would ensure that even if our machine crashed, we would know that, you know, if our entry is completely written or not, because at that point of time, our CRC would vary, right? So then we would say, yahan tak ka kharab ho gaya, let's move forward, right? So, and CRC has to be the first entry that we are writing, so that, like, we never write a bad value. Matlab, the first thing that gets dumped for a certain entry atomically onto disk has to be the CRC entry, and then key size, value size, key value. Because if any of that fails and the CRC is there, you can easily find out, my entry is not complete. So, you know, I can skip this entry altogether. Right. So your CRC has to be the first entry, which would help you detect if your system crashed at any time, and if your entry is genuinely correctly written on the disk or not, and if there is no chedchad being done with it. Yeah, Varun?
Is CRC like a hash code of the entire data?
Yeah. So CRC is basically when you use key size, key and value all together, and some fixed bytes represented. Let's say an 8-byte representation of your data. So it's a lossy way, something like an hash. You can treat it hash of all the thing that you have. So that's a CRC. So it's basically kind of checksum. That's CRC. Cyclic redundancy check is what the full form of CRC is. So you can also use checksum there. Okay, and you would obviously store timestamp to know this time pe entry was written. So just one meta field I've added. Okay, now how do we make our gets better? We can use something that we learned while doing the word dictionary wala part, right? To make get better, we have, like, we may put order 1, we may delete order 1, but now what we want to do is we want to make gets order 1. To make get order 1, we want to do pointed queries. Let me take a question. Yeah, Bhupendra.
Arpit, can you just repeat like the CRC part? So we write the CRC, then we write everything, and let's say when we are writing the value, the machine crashes.
Machine crashes.
How would I know? Like this
Okay.
CRC
So what
is
would you
written,
do?
right? How?
Okay. So let's say your machine, I have the diagram here. Let's say your machine crashed this time, and here is your CRC which is written. Okay. If your CRC is written here and your machine crashed at this point, your CRC is something that you have already computed, right? You have computed CRC using your key size, value size, key, and value. You can apply CRC, you can use checksum, any like fixed byte size representation that is a hash of.
CRC won't match the current value.
Won't match the
have.
current one. So what? So here you might see some other thing which is being written. When you read this key size and this value size, you are basically intruding into space of other. Right? And your CRC won't match. And that's when you would find that you have a corrupt data.
Got it.
So this is how CRC will help us identify. So it would not help us correct the data. It would just help us identify if something is corrupt or not. That's it. Right. So yeah. Now coming back to making gets better. We did make our put and delete better. Now it's time for making get better. Something which we did with our word dictionary, like we wanted to get is nothing but like your pointed lookup, your pointed query. Since our database up till now does not really have ability to make pointed queries, what we need is we need indexing. Like indexing, if we do on top of our data, we can make pointed queries. So what do we do is, let's say we maintain an in-memory hash table, not on disk. Let's say we maintain an in-memory hash table. So in-memory hash table where you store key and offset, something that we did with word dictionary. But what do we do is, let's say this is our append only file, which is like the way we are storing it, like a CRC timestamp, key size, value size, key and value. And what are we storing is, in this thing, we are storing this key K1 stored at offset O1. So anytime the entry gets updated, you have just one in-memory hash table where all of your keys are stored, against which offsets are stored. So whenever, so let's say I've written key K1 here. So first it would be like key K1 pointing to this location. Then I wrote K2. So K2 would point here. Then I wrote K1. So my K1, which was pointing to this location, would now point to this location. Right. So every time you are writing it onto the disk, you are also updating an in-memory hash table with the starting index where your writes have begun. So this way, you can maintain a very simple in-memory hash table that points to the most recent occurrence of the key in the file. Right. So now this is something that we can leverage to make our order one lookup. Because now what gets would do is, whenever, okay, let's go to this. So now whenever we would want to make gets over here, let's say I want to get key K1. So I would come to this in-memory hash table. I would go to this K1. I would find offset O1. Offset O1 is here. I'm going to this place and then reading the entry. Similarly, if someone asks me for key K3, I'll come over here, get the offset O3, go to the file on this offset and read the content here. Right. So it would store the offset of the latest entry in the file. And if the entry is deleted, you would have a special value against which, so it would be handled in the application that if I get this value, it means the value is deleted. Right. So once you get the data, once you get the value, you can have that check. Okay. So this in-memory hash table is something that we can leverage. Right. So this way, with this in-memory index, we now support pointed queries. So our gets are also order one. So one get is equal to one in-memory lookup on this hash table plus one disk seek, because like you have just one magnetic disk which is continuously writing, but when you're getting a data, it would do one disk seek to go to that offset and one disk read to read that chunk from the disk. Right. So now your gets are typically also faster. So this is the bare minimum that you can do to read a certain data from this file. Right. So one memory lookup, one disk seek, and one disk read. But what's the limitation? Is the only limitation we have is our index should fit in memory. So if we live with that limitation, we are getting a very, very, very high performance out of our system by just having a log structured storage. Right. So if we just live by this limitation, so our key, so you can only hold keys as much as you have RAM. So your all of your keys should be
fittable, should fit very easily in your RAM. If you can live with that, then you can have a very high read, write, and delete performance, like all three order one. Right. So, okay. Any questions till this point? Like, this is very similar to how we designed our word dictionary. Like, a lot of concepts are picked from there to here. Like, we didn't have indexing, we wanted to have pointed queries, so we built our own indexes, and we just lived with one constraint. Let's say our hash tables can be stored in memory. Right? If we live with that, we have a very high performance. Right? But the problem would that be like our main file where we are appending all the entries, it grows too big. If it grows too big, what would happen is, every file would have a limit. Let's say on a 32-bit file system, you can max have like 2 terabytes long file. And once it hits that, you cannot write more to that file, right? So if you have that kind of system, you also need to take into consideration like your file cannot grow too big. So it's very easy for any log structured system to explode in terms of storage, because updates are also insertions, deletes are also insertions. So everything is just insertion, so files would grow high. So to solve this problem, we rotate the file, which means once a file hits a certain length, let's say 50 MB, you create another file and start writing to it. So you have started writing to a certain file, and there is one process who is actually keeping an eye on this. And it says, "Arey, my file size went like 5. It went to the maximum limit that I'm allowed. Let's say 50 MB. So I'll start writing it to another file, and then another file. So this way, instead of having one gigantic file, you are having hundreds of smaller files, right? So this way, you have basically vertical scaling, horizontal scaling wala part hua. So one massive file ke jagah, you are having a bunch of smaller files. So you would set a threshold past which the file is rotated. Old file is made immutable, because like you cannot write onto that file. You can only read, because like you might have a latest entry of a certain key present in an old file, because wo entry pe kabhi write aaya hi nahi. If you have that kind of a thing, you would always need to allow reads to happen on that file, but no updates. Right. So this means we need to have one file which is active at all the time, on which writes are going, and all other files are made read only. On all other files will be happening, and each file is, let's say, 50 MB long. Once it hits 50 MB, you mark it as immutable and create another active file. Right? And then when that hits 50 MB, you create another file and mark the previous one as immutable. This way, writes are always going in one file, which is the active file. Now, when you have multiple files, that in-memory structure needs to like change a little bit. Instead of having key and offset, we would also store the file ID or the file descriptor. So key pointing to in this file, in this offset, you'll find the data, right? That's what we have to change. So key K1, we store the file ID on this value size. So this is our in-memory index structure. This is not on-disk structure. This is in-memory structure. So in-memory structure means storing key, and instead of storing offset, so vpos is the offset, and you'll know why I've used this kind of convention. So vpos is the offset, vsize is the value size, file ID. So on this file, in this offset, I've stored something, and it would point to a certain file. There might be another entry K2, which points to this active file pay. On this file, this offset at this timestamp, this entry is stored. Right. So we just extended our problem to like having multiple smaller set of files. But if we have a lot of smaller files, now what? We are wasting a lot of space, because you can actually, there would be a lot of entries which will never be used. Like something that is only there in the in-memory hash table is something that is relevant. All other things is junk, because you will never be making queries on that. Right? Let's say key A got changed 100 times. So first 99 entries would never be queried. The only entry that would be queried for get would be the 100th entry. So we have to remove all of those entries to save space, which is where we again use the merge sort ka logic. So we typically use merge and compaction. We merge all the immutable files into one. So once a while, we'll have a job where we are merging all of these files into one, right? So that we save space. And this is something that becomes very critical. So we do merge and compaction once a while. it could be once every 30 minutes, once every hour, depending on the throughput that you are serving. You'd have stale entries which are skipped and deleted entries which are skipped, right? So stale entries which would never be solved, like A updated 100 times, so first 19 entries won't be written, only 100th entry would be written, while other entries are deleted, right? And while doing this, at the end of this process, the data files, they will have the live and the latest version of each key. And when the files are merged, the offsets will change. So your in-memory index will also needs to be updated. And all of this thing needs to be done atomically for each key. And this is typically the merge, a very classical merge and compaction process where you have a lot of sorted, but at that time it is not sorted, but it is sorted by time because chronologically, because chronology is native. So you'll go through them one by one, and just keep on updating that in-memory index about it. Right, key, these are all merged, new offsets, and then you merge it into your live index. Like as simple as that. So once a while you'd have to do this merge and compaction. You will skip all the stale entries, you'll skip all the deleted entries, and then update your in-memory index with the latest offset and write the new file there. And for each key, this needs to be done atomically. Any question?
In the previous one, why do we store the key size in the? We can just show the offset, right? Why store the v size and yeah,
here, right? V size.
Yeah.
Even I don't know. I'll come to it from where did I pick this? Even I had the same question. I looked out for internet. I looked into a lot of sources, but I couldn't find. But the one line justification for that is like when you know the offset on which you would have it, if you know the v size beforehand, they ran an optimization around that. That's what they've written. They ran an optimization around it. Even I was like, sure, because now that you are being pointed to your in-memory, you are being pointed to the start of that entry, you can just read the first few bytes and get that information. But my best guess was like, I might have misinterpreted what they would want to say. Is this v size is not just the key ka value size. It's the size of this entire entry. Right, key in one shot, I would read those many bytes. And within that, I would have key size and value size.
Okay.
Got it? Because when you have your in-memory, that this is the file, this is the offset. But how many bytes would you want to read? Right, that length. So although they called it VSZ, basically value size, it has to be this entry size. That's what my best guess is, and that makes more sense than storing a value size over here. So that is my interpretation, because like when you write a code, you would need to know like how many bytes you would want to read. So wahan pe ye cheez kaam mein aayegi.
Got it. Yeah.
Thanks.
So,
Yeah. So just more like entry size. So this is the offset. This is the length of the entry. Read this entire thing. Usme you'll have CRC, timestamp, key size, value size, key and value on that disk. तो वहां से वो हो जाएगा.
So why do we need timestamp there? That's
वो उन्होंने उसपे भी एक ही लाइन लिखी थी. They just wrote this one line where they said that they can easily check if the entry is stale or not. Like I don't know why, but they just wrote this one line. I was even sure. This at least this made sense to some extent, but this timestamp never. But they just explained it well. And I just pointed to the exact source. I went through a lot of resources on the internet, but I couldn't find a good justification for timestamp, because like, why would you even want to store a timestamp for that? Like something that they would, if they would want to like, if their use case is like to immediately serve it from in memory, when was this last updated or something? Just like that. Otherwise, there is no sense of having to store timestamp there.
Yeah. So, I mean, if I understand correctly, the file rotation happens in the same process, and the compaction also happens.
Another process, because file rotation cannot happen on the same process. Otherwise, your write throughput will take a hit.
Okay. How can it rotate?
Symlinks.
Symlink. Okay, soft link basically.
Soft link. Basically, you will create a soft link to that file. So the writes would always go to the soft link. Soft link was pointing to old file. Then it got rotated. The new file was created. Soft link got changed to another file. So writes are never affected. Yeah, I had this exact same question, so that's why I wrote the code to actually simulate this and see this working. So that's what I'm like so sure it works this way.
Okay, then I have this question. How can we, okay, I mean, there is a possibility of CRC check failure in this. I mean, while this rotation is happening because it's independent, right?
But if you ensure atomicity, that won't fail.
How?
I agree कि CRC failure मतलब when the write is happening, but in most cases disk writes are atomic. So the disk IO that you do is atomic. If that disk IO is atomic in nature, then this problem is avoided. And in most, unfortunately, I ran it on SSD. I didn't run it on magnetic disk. On SSD, this sort of disk writes are atomic. So वहाँ पे problem नहीं आता. But you can definitely put the original paper suggested that they run it in the same process. But when I went through the implementation, they run a different thread that, well, although it's part of the same process, but they run it as a separate thread that does this rotation.
Okay, okay. During the compaction, it's in a different process, or it's.
No, compaction could be same process.
Yeah, because they have to update them.
They have to update the same in-memory hash. So they have to do it in the same space. So at that time, when the compaction appears, so basically think about compaction as a garbage collection, right? So you would have a big GC pause at that time.
And also we are removing duplicates out of all files.
Yeah. Okay. But even for the CRC wala thing, I had this thing. So when I ran the benchmark, I ran on SSD and I didn't see it. But with magnetic, there might be the same thing. But again, when I went to the source code, they are running it in a separate thread. I'm not sure why, but they are doing it. So the paper and the implementation seems little off-handed. But we can definitely check that. Okay. So with respect to this implementation, a lot of things like the only limitation is like keys must fit in memory. But what do we get? We get low latency per item read or written. So get is order 1, put is order 1. We get very high write throughput and also read because like read is also order 1, write is order 1. So your IO will starve because like your disk IO would hit its maximum. Your network IO might hit its maximum. Like your IO starvation would happen. Like your process is waiting for IO to happen, but IO is not happening because like IO is like so overwhelmed, which is a good thing because you are reaping 100% performance out of the resources that are available. Because minimal disk head movement, no reordering of items, like no rebalancing of those complex data structures. So everything is just doing the pure work that it is intended to do as part of your engine, right? So no dummy writes happening here or there. So you get a very high performance out of it. Single seek retrieval, get and put has a predictable performance. You have easy crash recovery using CRC, rather crash detection, not recovery, but a crash detection with CRC. Only tail could be corrupted due to partial writes. Like because upper ke writes are done, so only final write would be affected by it during crashes and all. And backups are very simple, like just copy paste the files that you have within that folder and your code is and your data is backed up. This database that we just talked, this storage that we just talked about is nothing but a Bitcast. So this is a very famous database called Bitcast. It's one of the most efficient key value store out there, and it actually handles production grade traffic. It is a backend of a database called Riak, R-I-A-K, and this Riak is used by Uber in production. So Uber uses Riak. Riak ka backend is Bitcast. So Riak is a distributed database, distributed, and basically it is sharded database. Each node of that database runs one instance of Bitcast, right? So that one instance of Bitcast, so pura file, pura storage happens locally. All the keys of that Riak instance, of that one instance of Riak, is stored in memory, and then you have multiple such instances out there. And this is what Uber uses to run their main primary driver or their ride platform. As they mentioned it in their blog post, they're using Riak backed by Bitcast. So each node of React runs one instance of Bitcast. So we just designed Bitcast, and basically that's exactly what the name of the paper is, from which I went through all the internals of it, how it is actually implemented, and the code is also available on GitHub. So you can also go through it and see how it is actually implemented. From that, I found out what threads use karte hai now. But yeah, this is what Bitcast, React, and Uber. So it had a lot of great things. It was a great introduction for, like, log structured systems and how you can, leverage you can build a very high write throughput and obviously implement a read throughput system on top of that. Okay. Any question around this? Basically, that's what I wanted to cover as part of log structured systems and storage engines first thing. Word dictionary and this, if you see, both the designs were very similar to each other, but very different context. So if you knew one, you could like think about like building another one, but you can see like how, but yeah, now you could be very comfortable while reading LevelDB, RocksDB, any embedded databases in general. And also while designing any file or while designing any file system, basically, any file formats like JPG, PNG, MP3. If you are expanding into that, you can find a lot of things are picked from all of this thing. Header format, then this, how are they optimizing reads on that? So how JPG optimizes image rendering, how are they storing it in multiple frames? You can explore that part. So this lays a very nice foundation if you're building any high-level production grade system, building storage engines. Like I've used quite a bit of this while at Amazon. Like we were using RODBs a lot, read-only databases, and petabytes of ingestion was like a piece of cake for a system like this. And obviously, as confirmed by Varun, Kafka's backend or their writes, they have a very high write throughput only because it is log structured writes. So this forms a great place to, whenever you need a very high write throughput kind of system, always add this concept that your system has to be log structured, and then try to model your system around it. So that's all I've wanted to cover today.
This LSM trees, right? Log structured merge trees, are they similar? Are they based on the same?
They are based on the same
idea.
Exact same thing. Instead of having just one layer, they just have multiple layers of it, and the writes always go to one layer and then they merge and then they merge and then merge. So once you have this thing, you can go through LSM trees and you'll find it to be a piece of. It's just about having like multiple tiers of it.
Okay.
Arpit, in this case, like we were wondering like a timestamp thing, right? So let's say we have two segments on which like people are writing, okay, and this is handled by different servers. Like let's say it is sharded and it is like A to Z, A to B is handled by two servers internally. So in that case, we will need timestamp because in one file, like a string called Arpit can go, in another file also it can go. So
this is all part of one process. You cannot have two processes writing it to the same file. It's all part of one process only. It's an embedded database.
When we are talking about segments, different segments we are writing. And when we are in LSM trees, like we write in a different segments, like segment A, and there are different segments. In different segments, people can write, right? That time we will need
one process. So you mean to say a multi-process, basically multi-threading, two threads writing it on the same
segment.
file.
Yeah, different segments. Then we'll need timestamp.
In order to identify which one came second.
The latest, yes.
Could be. If you're having something like this, like could be. Like then basically timestamp becomes that key through which you would identify, okay, this one came last, so the first one would be overwritten.
Yes.
Yeah. Thanks for clearing this up. I'll definitely read more about this and just go through it. But yeah. So when you say segment, it means that I'm getting like two writes at the exact same time, and I'm writing it on two different files, is it? Or on the same file?
No, like when segments, like in files, there are different segments. So eventually you're writing into two different files. Let's say like only one server can't handle all the writes, and people do distribute it. Even like A to C is there. Like even we have sharded it from A to C. You can't have like, if you have very write heavy system, you can't have one server like
Yes.
writing A to C. Then you have to distribute it, right? Even A to C
Acha,
you have to
okay.
distribute it. And once
Okay.
you distribute it, like there can be like, since it is sharded also, but distributed and sharded
But
also,
distribute. Got it.
then you need to have timestamp.
But
In order to find older and
ultimately,
younger part.
but ultimately it goes to the single partition,
Single
and
partition.
ultimately whatever your write log contains the last value, it's the one that's, I mean,
It would always contain the last value. Matlab, you don't need an explicit timestamp, na?
Yeah.
Because like you would always, like, since you're always updating the entry, the last one would anyway replace the entry. Matlab, you are never trying to do a manual conflict resolution, since it is one process, one data structure, updates flowing in, and obviously
One file.
since it is one CPU, it will always be like sequential, one after another after another. So the last one would always win.
No, I was thinking about, like, let's say A to C is there and we have two servers, okay? And two servers are writing on the same location, let's say file A and file B. And there's another job like that reads from that file and then builds that hash table. Because one will handle writes and another thing will read it at least.
So you're talking about multi-master scenario, Raman?
Yes. Like a system that is writing can't read it. Like they just have to write and someone else will be reading it. You know, while reading from two different files, like two servers can't write to the same file. They have to maintain till what time I wrote and then those things.
Okay. Still not clear. If you have any research around this, do share.
Sure.
This would be an interesting read. Definitely, this would be an interesting read. Why would we require this? Because in this specific design, it's just one active file. You would have one process that is doing writes and reads and deletes. Everything is handled by one. So and since it is all sequential, and then it would be serialized. It would be done sequentially. Somehow it would be done sequentially because you just have one CPU being consumed over.
Right.
So,
Now, Arpit, in this, like insert will be log O of 1, but like since like get and delete will O of 1 or log n only, not O of 1.
मतलब वो इन मेमोरी हैश टेबल लुकअप
Yes.
वाला
Yeah.
मतलब वो निकाल सकते हो, वो भी वहां पे लॉगिन हो जाएगा, बट ठीक है. Got it. Yeah.
How is it login hash map? It's average cases.
Its average case is order 1,
But worst is log n.
yeah.
Anyway, you have to do binary search again on the hash table to get those keys or like which you want to update. So most of average cases it is O of 1, but worst case one has to do the binary search and
Binary search one. Yeah. So internally the hash table would have to do binary search to locate the key in that hash table. That would be order login. But in general, for some reason, even Python, JavaScript, everyone says that our lookups are order 1, which is average case. So they all like boast about it. So that's where I'm like, chalo, order 1. So
And
hash
they
table
expect,
lookups, everyone says order 1.
yeah, they expect their hashes to be good.
Yeah. Like basically Python is built on top of Python dictionaries. Matlab, every single thing, classes, objects, and whatnot, everything is a dictionary. So because of which a lot of emphasis they have put to optimize the dictionary lookups. If you go through the C Python source code, you'll find so many optimizations done just to make the dictionary lookups like really, really efficient. I've been spending like 3 weeks to understand that code. I'm still unable to do it. I found a book that explains it. I'll go through it once. How they've and they have actually explained how it is order 1 on average. How they've reduced that. And they have actually code off to run benchmarking on that. And you would find it to be order 1. I'll do that. Nice. Fascinating. So this typically concludes storage, but actually not concludes storage engine, but S3 is something which is remaining, which is a very interesting design. We'll use S3 as a spillover for the next week. So this happened in the last code. So first is my S3, I was able to close it, but usme word dictionary I didn't cover in depth. That's when I got that feedback. So then what I did, I'm using S3 as a spillover for the next week. So next week, Saturday, first half will go into S3, and then we'll continue a discussion on to high throughput systems. So S3 का big design पूरा research paper पढ़ के किया है वो सब. So I'll be explaining the entire S3 part of it. ठीक है. Awesome. Okay, thanks a ton, guys. See you guys next Saturday, where we'll discuss S3 and high throughput systems. Okay.
Thanks,
Thanks.
Arpit.
Bye
Thank
bye.
you.